Experiment 1. Coulomb's Law.
Introduction. Coulomb's law is the magnitude of the electric force that a particle exerts on another is directly proportional to the product of their charge and inversely proportional to the square of the distance between them. Mathematically, the magnitude of the electrostatic force acting on two charged particles, which is Q1 and Q2, is expressed as Fe equal to K times Q1 times Q2 divided by R square, where R is the separation distance between the charged object and K is a constant proportionality called the Coulomb constant, which is K equal to 9.0 times 10 to the power of 9 nanometer square over Coulomb square. The objective of this experiment is to satisfy Coulomb's law experimentally and to study the parameters that affect the electric force and to find experimentally the electric constant K.
Procedure.
Part 1. Open PHY by using the link given in the lab manual. Then fix the charge Q1 and Q2 and work the values in the table. After that, the distance between two charges are changed as shown in the table 1. Value for each distance are recorded, and in the table 1, after finding R square and 1 over R square, the value are filled in the table 1. Part 2. Open PHY by using the link given in the lab manual. Q1 being controlled and fixed at 5 microcoulomb, and the distance between two objects are fixed at 6 cm, then being recorded in table 2. The charge of object 2 changed as shown in the table 2 and the electric force were recorded in the table 2.
Data analysis.
Part 1. From the paragraph, we can see that electric force is inversely proportional with R. We can see that as the R increase, the electric force will decrease with the constant of changing Q1 and Q2. For the second part, based on the plot graph and collected data, it clearly shows that electric force is directly proportional to the charge Q2. You can see when the charge is increasing, it same goes to the electric force also increasing. So the relationship between electric force and the charge is directly proportional to the charge Q2. Discussion. As for the experiment 1 of Coulomb law, we have already studied the parameter that will affect the electric force and also to find the electric constants experimentally. The experiments are done to verify the proportion of Coulomb's law, which is the between of point charge Q1, Q2, directly proportional to the product of the charge and inversely proportional to the square of the distance between the two charges. An error that we could detect from this experiment is from the measurement error, but we could improve and avoid the error to get the data accurately by taking a few measurements between the two charges. Other than that, we should also repeat the steps for both parts. In experiment for part 1, we should discuss about the result of questions that are given from this experiment. From the plotted graph that has been collected from the data in the table 1, as the 1 over R square is increasing, the points of electric force are also increasing. This has shown that 1 over R square is proportional to electric force. From the graph, we could also find the electric constant of experiment part 1. Given the Q1 is 1 times 10 to the power of negative 6 Coulomb and Q2 is 4 times 10 to the power negative 6 Coulomb, by using the formula S equal to K times Q1 times Q2, the electric constant that we calculate is 8.9879 times 10 to the power of 9 nanometer square over Coulomb square. As the given K, which is 9 times 10 to the power of 9 nanometer square over Coulomb square. So, to find the percentage error in electric constant, we use the formula percentage error equal to experimental theoretical divided by theoretical times 100%. As the result, we get 0.14% of percentage error. This shows that parameters are affecting the electric force and electric constant, but the result data that we get from the experiment are still acceptable. In experiment 2, from the plotted graph that we get, we could say that the Q2 is proportional to electrical force. This is shown as Q2 is increasing, the electrical force is also increasing. The electric constant are calculated based from the graph. As using the formula Fe equal to K times Q1 times Q2 divided by R square, the result for electrical constant that is 8.99 times 10 to the power of 9 nanometer square over Coulomb square. The given K known is 9.0 times to the power of 9 nanometer square over coulomb square, we use the percentage formula, which is percentage error equal to experimental theoretical divided by theoretical times 100% to find the percentage in K of the experiment. The result of percentage error that has already calculated is 0.001%. We could say that the parameter is not really affecting the electric force and electric constant for the experiment. So, the data that we get from the table 2 are acceptable. Conclusion. This experiment was performed to satisfy Coulomb's law experimentally. The goal of this experiment was to find experimentally the electric constant using PHY. PHY were important tools in the experiment. Without doing live experiment, PHY being used to show the virtual simulation. The final data shown on table 1 and table 2 were uniform in numbers. From table 1 on Q1 column, data will decrease in number, while on Q2 column, it showed that the data will increase in number. From table 2, the data showing that the number decreased. The possible error in the experiment was random error. Random error can be reduced by averaging a sufficiently large amount of results. In this experiment, one can state that the results supported the hypothesis.
Experiment 2. Capacitance. Introduction. When a capacitor is connected to an EMF, which is E, the plates attain charge from the terminals of the battery. The amount of charge is governed by the geometry of the capacitor. For a parallel plate capacitor, the capacitance is given by C is equal to K EMF E over D, where A is the effective plate area, the area effectively overlapping, D is separation of the plates, EMF is the electric permittivity of free space, and K is the dielectric constant for the insulating material in the linear plate region. In this lab, we will investigate this relation. First, we will keep the separation constant and vary the area. In this case, the plot of C against A should be in a straight line with a slope given by M is equal to K EMF over D, which M is a gradient or slope. Then, we will keep the area contact and vary the separation. Here, a plot of C against 1 over D should be a straight line with a slope given by M is equal to K EMF E, which is M is the gradient or slope. The objective of this experiment is to study the capacitance varies with the separation between the plates. The second one is to study the capacitance varies with the area of the plates. The third one is to study the dielectric effects on the stored charge, energy, and voltage between the plates of the capacitor when it is connected or disconnected from the battery. The procedure part 1 is paper from the choice of dielectric EDB was selected on the right hand side. The dielectric was inserted completely inside the capacitance. The capacitance was checked to see the capacitance meter. The battery could be either connected or disconnected for this part. The second one is the values of the plate error A initial. Initial it should be the smallest possible, and the distance between plates initial. Initially, it should be largest possible, and corresponding capacitance were recorded. The third one is the plate area was slowly increased, and the corresponding capacitance were measured 4 more times. Results were recorded in the table. SI unit were used for all measurements. Excel or other software were used to plot capacitance as dependent variable against the area. Then, unit regression was used to draw the best fit line, or as known as trend line, to approximate the data with the linear model. The screenshot of the graph was inserted below. It contained label axis and unit. The second one is data points and best fit line. Remember that the best fit line does not necessarily go through all points, but approximately the trend. An equation of the best fit line is contained in the graph. The procedure in number 5 is the area was restored to initial. The separation between the plates was slowly decreased, and the corresponding capacitance was measured 4 more times. Results were recorded along the focal of the separation. And the procedure number 6 is SL or Other software was used to plot capacitance as dependent variable against the reciprocal of the relation between the plates. Then linear regression was used to draw the split line, also called as trend line, to approximate the data with the linear model. The screenshot of the graph was inserted. It contained liberaces and units. The second one is data points and best fit line. Remember that the best fit line does not necessarily go through all points but approximately different. And the last one is equation of the best fit line. This is the result of part 1 in this experiment. You can see the plate area, and this is the result of area, and this is the capacitance. We can see that plate's area is increasing and the capacitance is also decreasing. This shows that they are directly proportional to each other. And then this is the graph of capacitance versus plate area. When we plot the graph, we can see the plot here, and we can see the gradient. We will find the gradient, and we can see the graph is directly proportional to the axis y and axis x. This is the result part 1 of the distance between plates and capacitance. This shows that decreasing of distance between plates but capacitance is increasing. This shows that this is indirectly proportional to each other. This is graph capacitance versus distance between plates. This shows that it is directly proportional between capacitance and distance between plates. Or the other words, we can see graph capacitance is directly proportional to distance between plates. Okay, in this analysis part, we can determine the gradient, or we call as slope, and we got 3.7 to the power 10 times 10 to the power of 40. Okay, this is the graph, and this is when in the analysis part, we can see the percentage. We can find the percentage error, and we got percentage error is 0%. This shows that our experiment is accurate. Okay. In the experiment discussion part, the role of this experiment tool, which is capacitance varies with the separation between the plates, and also the capacitance varies with the area of the plate. The second one is the electric effects on the stored charges, energy and voltage between the plates of a capacitor when it's connected or disconnected from the battery. This experiment is done to provide the amount of charge controlled by the capacitor when a capacitor is attached to an E, which is at EMS, and the plate attains charge from the terminal to the battery. The experimental error in this experiment is measure error, but this experimental error was overcome by managing the error from recurring by taking a few measurements and also repeating the step correctly. Okay, from the discussion from the experiment, this experiment part 1, we could get the result and graph plotted. From the graph, we can see that the capacitance is increasing when the plate area is increasing. This is showing that capacitance is directly proportional to plated area. And we could find the dielectric constant by using formula which is M equal to K EMF A. The dielectric constant, which is K, that we calculate is 2.7 times 10 to the power of negative 40. As the value of the dielectric constant K, we could also find the percentage error for this experiment, which is 0% by using the formula.
Okay, next, this is the procedure for part 2. Firstly, the value of the plate area and the plate operation were revert to the original, and the dielectric was removed entirely from the capacitor. The capacitance, charge, voltage and energy meters were showed by checking off approximately boxes on the right side the simulator. Next, the battery was connected and the battery voltage was turned on to about 1 volt. The third step is the dielectric was inserted slowly inside the capacitor. As the dielectric fills more space in the capacitor, the change below were observed and recorded, like capacitance, charge, voltage between the plates, and energy stored by the capacitance. The step 4 is the dielectric was removed entirely and the battery was disconnected. Step 3 was repeated and the change below were recorded. Capacitance, charge, voltage between the plates, and the energy stored by the capacitor. Alright, now this is a result for part 2. Alright, from the graph capacitance versus distance between plates, we can see that the capacitance are proportional to the distance between plates. Alright, from this experiment, they have 2 questions. The first one is, if the battery is connected to the energy of capacitor battery system constant throughout the process of inserting the dielectric, explain the change of energy if any. The answer is no. The electric field from the dielectric will partially cancel the electric field from the charge on the capacitor plates. If the battery is connected to the capacitor, the battery is able to store more charge in the capacitor and bringing the field back to its original value. The second question is, if the battery is disconnected, does the energy stored in the capacitor remain constant as the dielectric is inserted? The answer is no. The energy is decreased. If the battery is disconnected, the charge on the capacitor is strength on the capacitor plate, so it not remain constant and the dielectric increase as capacitance. Next, the discussion for data part 2 is, for the experiment part 2, which is effect of the dielectric on the capacitor, we can discuss from the results of the questions and the graph plot. From the graph plot, which is graph distance between plots and capacitance. From this graph, we can see that distance between plates is proportional to capacitance. This was proved when the distance between plates is increasing. The capacitance is also increasing. This graph is directly proportional from the first paragraph. For the question that has been asked, if the battery is connected, the energy of capacitor battery system will not conserve throughout the process of inserting the dielectric. This is clearly because when the battery is converted to the capacitor, it will be able to store more charge in the capacitor and through the original value to the field back. Another question that need to be solved is, if the battery is disconnected, the energy stored in the capacitor will not remain constant as the dielectric is inserted. This is because the capacitance is increased as the dielectric is inserted and the energy stored in the capacitor is decreased. Alright, the last one is conclusion. As for conclusion, we know that the objective of the experiment are fully achieved, which to know the capacitance varies with the separation between the plates, with the area of the plate, and to know the dielectric effect on the stored charge, and voltage between the plate of the capacitor when it is connected or disconnected from the battery. The result showed perfectly various, and based on the both of the graph that has been plotted, we know that the capacitance directly proportional to the plate area and the capacitance is also proportional to the distance between plates. From the result on the table show that the data increase except the random data. Since the charging and discharging were observed with the expected effect, the one of the proposed purpose of the experiment was achieved. This shows that an exponential process, charging and discharging. The possible error in the experiment was random error. Random error can be reduced by averaging sufficiently large amount of result. The result was supported by the hypothesis.
Next, we will present about experiment 3, which is DC circuit. So, DC circuit is about Ohm's law. Ohm's law states that the potential difference, which is voltage, between the two ends of the material is directly proportional to the current flows through the material. So, the formula of this experiment is V equal to IR, where V is the potential difference between 2 points measured in volt, R is the resistance of the element measured in ohm, and I is the current flows across the element measured in ampere. The objective of this experiment is to ensure the current and voltage for simple DC circuit, to study series connection of resistors, and to study parallel connection of resistors. So next, I will explain about the procedure. The first part is measuring the current and the voltage in simple DC circuit. First, to get familiar with the function of each part, we take our time working on the simulation by using the link given. As shown in figure, the battery symbol in the bottom right of the screen and show current is clicked on. And a simple DC circuit contains of a battery, resistance, switch, and wires. The voltmeter from the right second box was selected and the two terminals connected with the end points of the resistor. The ammeter was dragged and it connected with the circuit in series. The reading of the voltmeter V and ammeter I was recorded in the data analysis. The values was clicked on and the resistance R was recorded in table 1. The battery was clicked on and the voltage changed to 20 volt. And then the steps of 5, 6 and 7 was repeated and the result V2, I2 and R was recorded in table 1. The voltage changed to 30 volt and the step 5, 6 and 7 was repeated. The result was recorded in table 1. A screenshot of the circuit was made and pasted in the report. So, this is the example of series DC circuit. The second part of this experiment is series connection of resistors. First, another resistor was grabbed and it was connected in the circuit in series. The power supply output was adjusted to 120 volt and the two resistance to be R1 equal to 20 ohm, R2 equal to 30 ohm. The voltmeter was connected across the R1 to measure the V1. The voltmeter was connected across the R2 to measure the V2. The voltmeter was connected across the power supply to measure the total voltage. So V1 plus V2 were calculated and it was compared to the total voltage across R1 and R2. The electric current I was measured. The ammeter was used before R1, between R1 and R2, after R2, and the result was commented. The product of I multiplied with R1 was compared with the value of V1. The product of I multiplied with R2 was compared with the value of V2, and the screenshot were pasted in the lab report. So, this is the example of series circuit with two resistors. Okay, the last part of the experiment is parallel connection of resistors. First, the circuit was connected as shown in figure. The voltage of power supply adjusted to 120 volt. The voltage V1 across R1 was measured using the voltmeter. The voltage V2 across R2 was measured using the voltmeter. So, V1 was compared to V2 to output from the power supply V total. The current I1 was measured through R1 using the ammeter. The current I2 was measured through R2 using the ammeter. The total current in the circuit I total was measured. So I1 plus I2 calculated and it was compared to the result in A. The data was recorded in the lab report and also the graph was based in the lab report. So this is the example of parallel circuit.
For the data calculation for trial 1, 2 and 3, we use the voltage of 10, 20 and 30. And the resistor calculation that we will get are all 10. The current in a circuit is directly proportional to the electric potential difference in pairs across its end and inversely proportional to the total resistance offered by the external circuit. So, the greater the battery voltage, the greater the current. For part 2 of the experiment, we use 48 volt for the first voltage and 72 volt for the second voltage. So, the V total we could get are 120 volt. The value for voltage 1 and voltage 2 are different because of its positions. The current is still remain the same because it is the series circuit. For the part 3 of the experiment, we use 120 volt for the voltage 1 and 120 volt for the voltage 2. The V total we would get is 120 volt. The total volt still remain the same because it is the parallel circuit. The current that we use for I1 is 24 ampere. The current that we use for I2 is 12 ampere. The I total for this circuit is 36 ampere. The result shows that the current is being split up into each loop because it is the parallel circuit. All the current that are available will flow through the ammeter and damage it, or it won't give any typical reading for the circuit being tested. A high impedance of the voltmeter will result in a significant voltage drop in that part of the circuit. So the value being shown is not the typical value of that part of the circuit. Rheostat can change the resistance without interrupting the circuit. A simple discussion about part 1 is when the low current is used, the low electric current is occurred, and as the high current is used, the high electric current is occurred. And the graph shows that the voltage is proportional to current. A simple discussion about part 2 is V total can be calculated by adding the V1 and V2, and the I total is still remain the same between I1 and I2 because of series circuit. From the graph also shown that the voltage is proportional to resistance. A simple discussion for part 3. The V total still remain the same, and the I total can be found by adding the I1 and I2 because of it's a parallel circuit. The voltage remain the same as the resistance increase. Meanwhile, the current decreasing when the resistance increasing.
Assalamualaikum warahmatullahi wabarakatuh. My name is Aisha Zulaika binti Jafri and I'm from group 4 and I will present the last experiment in physics 150 experiments which titled magnetism, and I will present this experiment to our lecturer Madam Maria Muhammad. Okay, so in this experiment it contain introduction, objectives, procedure, result, discussion and also conclusion. Okay, so we will begin with introduction. Okay, so what is magnet? Okay, so permanent magnets are made from ferromagnetic materials, which is electrons circulating around the nucleus behave like current carrying wire loops. Okay, so basically the field of single atom is extremely small, but if large number put together, it can be large. So how to turn ferromagnetic material to the permanent magnet? So basically the individual atoms or current loops must be preferentially aligned in one direction. So in this magnetizing process, putting the material in strong magnetic field. Okay, so the field lines continue inside the magnet but appear to emerge from one end and re-enter at the other end. So we can see in this picture, the end which originate is called north end and the other end is called south end. So the blue one is the south and the red one is the north. Okay, so for solenoid or a coil, the end from which the field lines appear to originate is north end, and the end toward which they point is called south end. Okay, so the convention naming of these two ends, north and south end, arises from the magnet's behavior in the Earth's magnetic field. We know that our Earth's crust has some permanent magnetization, and the Earth's core generates its own magnetic field. Okay, so if the identical magnets are placed near each other, they may be attracted or repelled depending on their relative orientation. So we know that the north end of one magnet will attract to the south end of the other, but two north end or two south end, if we place together, it will repel each other. We know that the magnet will not attracted to the same end. Okay, so what are the objectives of this experiment? We have two objectives. The first one is to find the field strength B in unit G by quantity of the loops. The second one is to find the field strength B in unit G according to the voltage V. Okay, so the next is procedure. Okay, so we know that to do this procedure in experiment, we need to click the link PHY simulation that given in the lab manual. Okay, so the first one, we need to click the button run now in that simulation. Okay, so the second, we need to move the compass around the bar magnet, and then we need to click flip polarity in the right menu of the simulation website, and then we need to click reset all button in the right menu. We need to check the box show field meter in the right menu, and a blue box should appear. Okay, so this measures the magnetic field around the magnet, which is known as B. The magnetic field is measured in Gauss, unit Gauss G, and you need to move the field around the magnet. Okay, so next, we need to move the meter so that it is about 1 inch on our computer screen away from north end of the magnet. Okay, so we need to move the meter the same distance away from the south end of your magnet. Okay, so at the top left of the simulation window, we need to click the electromagnet tab. The battery should be connected to a wire with loops that has current running through it. The compass needs to be around the electromagnet to make the experiment become smooth. So you need to click the show field meter in the right menu of the website, and the meter was moved around the electromagnet. Okay. Next, the meter need to be placed about 1 inch from the left side of the electromagnet. Okay, so we need to set the number of the loops in the electromagnet. We need to adjust, and it has in the right menu. So each number of the loops 1 to 4 need to be write down the field strength in the table. Okay, so you can see the picture, you can adjust there. And then lastly, the number of loops for the electromagnet need to set up back to 4 and make sure the field is still 1 inch from the left side of the coils. The battery has a sliding bar on it that lets to adjust the voltage in the electromagnet. So after you settle the procedure, the table that is given in the lab manual need to be complete. Okay, so there's a picture of one of the screenshot from the PHY simulation, how to adjust your electromagnet, your magnet and your meter and all. Okay, So this is result that we obtain from the procedure. So based on this data 1 and data 2, we can see clearly that when the loops increase, the field strength also increase. Same for both data 1 and data 2. Data 2 also, when the voltage increase, the field strength also increase. Okay, so this is some of the screenshots from the field simulation on based what we obtained from the result. Okay, so here we can see the meter and the electromagnet. So this is the result for data 2. Okay, so now we are in discussions. Okay, so what we discussed in this experiment. This experiment was held to demonstrate the effects of a bar magnet's magnetic field in relation to the distance away from the object. Okay, so the results show that the red part of needle points towards to the south pole. Okay, it clearly showed that it points toward the south pole. When the meter was moved closer to the magnet, the field will increase. Okay, the magnitude of field strength B was measured to be 4.78 gauss. Okay, so the amount of magnetic field for both north and south ends of a magnet are same. And the left side of the electromagnet of the south end, because of the red part compass needle point towards of the south end. So we know it clearly showed to the south end. Okay, so next, when we move the meter closer to the electromagnet, the field strength will increase. Okay, so the amount of field strength increase as we increase the number of loops in the electromagnet. We can see this on the data that I showed earlier. Okay, so the voltage is directly proportional with field strength in an electromagnet. Okay, so here the conclusion. So this experiment can be considered success from the result that shown and the objective that we can achieve, and how we could find the field strength according to the voltage, and the clear result about the amount of field strength increases as the number of loops in an electromagnet. Okay, so all the objectives of this experiment already be obtained and the hypothesis is accepted. So that's all from us. From 6 of us present our 4 experiment. So hope you enjoy and thank you.
Could you be the one?